Now we're going to talk about dot products. If you're sitting in a statics class, you've probably seen dot products before, I hope. There's a formal definition of a dot product, which is, if I have some kind of vector A that has an x component, a y component, and a z component, and then I have another vector that has an x component, a y component, and a z component, then theoretically I should know that the dot product of those two vectors are the x ones multiplied by each other plus the y ones multiplied by each other plus the z ones multiplied by each other. And that's the formal definition of a dot product. Again, I'm more of a pattern matcher than a formula memorizer. That's not true. I love memorizing formulas. But let me give you kind of an example here. So 2j hat, say, minus k. And then b was 5 minus 3 and 6. Then I would say that the dot product of these two would be 3 times 5 plus 2 times negative 3 plus negative 1 times 6, also known as whatever 15 minus 12 is. That would be 3? Oh, please, would that be 3? Okay. So the dot product would be 3. Something really, really important to note is that this is a number. You're like, no, I know it's a number. But I mean it's a number as in it's a scalar, not a vector. Not a vector, right? It doesn't have any direction, no direction. It just has magnitude. It is an aimless little number just running around. It's just like 3. I don't really know what I'm doing, but I'm a 3. That's a dot product. Totally different from cross product, which we're not talking about yet. But anyway, so there's 2 different definitions you can think about with a dot product. This is the definition that probably comes to mind first. Okay? But there's actually another definition of a dot product which is very, very useful as well, which is that the dot product of two vectors is also defined as their magnitudes times the cosine of the angle between them. Okay, so again, whenever I'm writing something like A, that's shorthand for saying the magnitude of the vector A. A is the magnitude of the vector A. B is the magnitude of the vector B. And so cosine is the angle between them. Like that. Cool? Got it? Okay. Now, if you want to prove this to yourself, let's pick some simple vectors. Let's call a vector 5, 0, 0. Whenever I write this, I mean 5i hat. So I'll just write it like this. So I'm going to write a vector that's 5i hat. And I'm going to do a b vector that's 5i hat plus 5j hat. Okay, so let's draw those out and say, okay, so this should be 1, 2, 3, 4, 5. There's A. 1, 2, 3, 4, 5. There's B. A is this vector, and B is this vector. Okay, so let's find the magnitude of A. So the magnitude of A is just going to be 5, right, because it's 5 long. Okay, and the magnitude of B is going to be the square root of 25 plus 25, square root of 50, which is 5 square root of 2. Okay, so the magnitude is B is 5 square root of 2. Now, theoretically, we should get that A dotted with B is going to be A times B times the cosine between them. So we can check. All right, A times B. Now, what's theta? Hopefully, you saw if this is 5 going this way and this is 5 going up this way, then this better be 45 degrees, right? Okay, so times the cosine of 45. Good. Okay, so this is 5, or 25 times the square root of 2. And we know the cosine of 45 is square root of 2 over 2, also known as 1 over the square root of 2. So those cancel out. So A dot B is 25. Now let's see if we get it doing it the other way. So now we're going to multiply corresponding elements. So 5 times 5 is 25. Remember, this is 0 times 5 is 0, and then the k components are also 0. So we get 25. So you get the same thing both ways. So there's two reasons that you're going to use the dot product. You're either going to use it to find the angle between two vectors or intersecting lines, or you're going to do some projections along a unit vector. Okay? Okay, so let me go ahead and write those out. These aren't the only uses for dot products. So some uses for dot products. One is to find the angle between two vectors. And this is especially useful. I mean, in 2D, you're like, well, I can just draw and figure it out. But in 3D, this is a lot more useful. So, you know, if you had some kind of a vector, you know, coming out this way, and you had some other vector, you know, going out this way, and you want to think about there's a plane, you know, coming out of the page, kind of cattywampus to you. That's the angle that we're talking about. It's the angle, the coplanar angle between these two vectors. So if you drew, assuming they would intersect somewhere, then you could draw a plane that contained both of those vectors in some kind of cattywampus plane. So call this cattywampus. How do you spell cattywampus? I have no idea. Cattywampus plane sticking out, and then that would be the angle between them on that plane. Okay, so that's one thing that we'll use it for. The other thing that we would use it for is to project a vector, project one vector along a unit vector. Okay? So let's take a look at that. What I mean by that, at least. So what I mean by that is, say we have two vectors, I'll call them u and v. Okay? And then I have some other arbitrary vector sticking out here, f. Okay? If I want to know the shadow, and whenever we say project, you want to think about project as being kind of a shadow. The shadow cast on that vector. So in 2D, it's pretty easy to see, I think, that if I cast a shadow, say, on the u, it's not very pretty. If I cast a shadow on the u, right there, I could call this f projected onto the u. So we call that sometimes fu projected, which is just kind of fun to say. Now, if you look at this, if you know that the magnitude of this is f, and if we want to consider a unit vector in the u direction, which I'm kind of running out of colors for, so we'll call this u, which is just a unit vector in the u direction. Then if I actually wanted to calculate fu projected, I could say, oh, well, that's just going to be f cosine theta, right, in the u direction. So let me show you that that's going to be the same thing as the dot product. So I think it's easier to look at it and say, okay, it's going to be f cosine theta in the u direction. Okay. So see what happens if we dot f and u. So if I dot f and u, I'm going to get the magnitude of f times the magnitude of u times the cosine of the angle between them. Well, I know the magnitude of u is 1, so that means that I'm going to get f cosine theta. Okay, so sometimes you'll see the fu projection, I don't want that there. Sometimes you'll see the fu projection as f dotted with u put in the u direction. Okay? Something like that. So you're giving it a magnitude and you're giving it a direction. Remember that the dot product itself doesn't have a direction. You have to put the direction on it. So this is, again, this is your magnitude and this here is your direction. Okay? So you can do the same thing for v if you want. You can project f onto the v-axis, and again, assuming you have some kind of unit vector along the v, and I could say, okay, so this is my fv projection. So I can project along fv. And again, fv projection is just going to be f dotted with v in the v direction. Again, assuming that v has a length of 1. That's what we mean by a unit vector. Okay. Now here's an important question. All right. Let me move this guy. So I'll have my very, very important question. There. Here's my important question. Does fu, which is just fun to say, projection plus fv projection equal f? Does this work? Okay. Generally, the answer is no. Now, the reason generally it doesn't work is because, let me just show you graphically why this doesn't work. So here's my v projection. So theoretically, no, what happened there? You go back where you came from. I still caught it. Oh, well. If I attach, over here. If I add these tip to tail, so this is my v projection. If I add it tip to tail with my u projection, I'm in no way going from here to here. That's not my f at all. Not even close. Not even like kind of sort of close. You see that? If I add them tip to tail, they do not match. Thank you. There we go. So, again, this is not going to be the same thing if I add them to tail. So the answer is generally no. Now, if u and v are perpendicular, this works. But in general, no. So, the idea is, well, if I've got a square, a perpendicular coordinate system, and I project one guy this way, and I project, well, I guess I wouldn't have projected him there. If I project this guy over here this way, and I project the other guy down, well then, sure, if I take this one and I move it over, they're going to add up, and that's going to be the resultant. But that's just because the u and the v, or in this case the x and the y axes, are already perpendicular. But if your axes are not normal to each other getting started, then this isn't going to work. Got it? Got it. So then the question becomes, well, what if I want to add things together? And in that case, you'd have to go in here and manually calculate some fu perpendicular, like that. Make sure you've got the arrow going in the right direction. So you could go ahead and you could calculate that and say, well, I know that I want fu, now my notes are just getting really messy, I'm sorry. I want fu projection plus fu perpendicular to equal f. So if I have the other ones, I can calculate my fu perpendicular as f minus fu projection. So if I really wanted to calculate it, I could. You just can't get it by doing the projection on the other side. It's kind of one of those classic trick questions that pretty much every professor asks at some point or another. And then what I would say is, of course, the most important thing that you can do, so adding this to our list, coming in at number 3, is using dot products to find magnitudes. Of vectors in calculators. So, say I've got some kind of a vector, 3, 6, and whatever, doesn't really matter, -1. So if I want to find its magnitude, I'm just going to write the square root of the sum of the squares, 9 plus 36 plus 1, so square root of 46. Okay, Well, see what happens if I take the square root of the dot product, right? So the dot product is I take each element and I dot it with the corresponding elements. If I'm dotting something with itself, that'd be 3 times 3, and 6 times 6, and -1 times -1. So if I take the square root of the dot product, I'm going to end up with the magnitude of a vector. So that's very useful if you've got something in here. So let's say I had this one already. Say I had 3, 6, and -1 in here like that. So if I wanted to get the magnitude of it, if you don't already have this capability in your calculator, go find my dot product, which is here somewhere. I always look in my catalog because it's easier. Dot product. So I could take the dot product of it with itself. So that would be the 46, and I could take the square root, take the square root of that. So taking the square root of the dot product is also a very useful thing to do with the dot product, to use it to find magnitudes. It's kind of fun.